because you're adding that to that, and you're adding that to that. And similarly this to this, and this to this. That's the definition of binary operation on ordered pairs when you have a tensor product. Okay? If you rusty, go back and have a look. Alright, so what about this one? So you're adding this to this. So that'll give you, and then you add that to that, so it'll give you a 1. And for here, 0 plus that, so that'll give you a 1. And then 1 to 0, that gives you a 1. Okay? And well, I'll do a few more. Okay, now this one. So you add that to that, so it'll give you a 0. And you add 2 to 0, so that's a 2. And then you add this to this. So you get 1, there's 2, so you add the 1 to there, so it'll give you a 1, 0, and a 1 and a 1, but it's mod 2, so this will be 0. Okay. And then a 0 to 0. Okay, and so on and so on, right? Now, so you choose only the, if you get a repeat, throw it out, right? Because remember the theorem that a group is equal to the union of disjoint cosets, left cosets, right? So what's the actual list? That's 1. That's 1. That's 1. Now this one is the same as that, right? And similarly, the remaining two are the same. So these three are your left cosets, and now you can rewrite that as Z2. And you can rewrite this one as Z2. Okay, so you got a 1 in here, so that's the same as this. And similarly, Z2 times, whoops, set. Right? Now, the order of this is 6, right? The order of Z2 is 2, the order of Z3 is 3, and when you have a direct product, the order is the product of these two, so the order of this is 6. Okay? So you'll have three cosets. Well, because the other 3 are the same. So, right. So pass on. You're given the subgroup of the integers. So question 5. I'm doing a bit under half of them, I guess. So you've got the subgroup of the integers, binary operation, just ordinary addition. And that's a subgroup of reals, right? Again under addition. Okay? And hang on, what is the question? Yeah, question 5. What are the left cosets of Z? So this is your subgroup of this bigger group. This is the set of all reals, the set of the integers. Right? So obviously this is a subset of that. It's also a group, so it's a subgroup. So, what are the left cosets of that? Well, let R be any real, so it'll belong to this group, right? So in general, and the binary operation is plus, so let's find the left coset. So it'll be of this form. So R plus Z, effectively, right? That's your left coset. That's your element of your group, general R's. Okay, that's your subgroup. That's your binary operation. So it's sort of like G of H. This is your H, G of H. All right. Now, now in general, R will be of the form some integer n plus x, and x will be less than 1 and greater or equal to 0. Do you see that? Does that make sense? This is just any old real. Okay, so you can rewrite that real as some integer plus some amount that's whose absolute value is less than 1. Right? Less than 1. So you can rewrite that. So you can then read this R plus Z is then just n plus x plus z, right? But this n gets absorbed into z because it's one of the integers. So you can just rewrite this. This just then just becomes x plus z, right? This is an integer, and this is the set of all integers. So this z includes that n. So you don't need to put it separately. So you just have this. Okay. So that's it. That's your that's the set of all left cosets of this subgroup, and where x is is less than 1 greater or equal to 0. Okay? You can write any real in that form. Okie dokie. Question 7. So you've got a group G, you've got a subgroup H, and you're asked to prove that if x belongs to YH, in other words, if x is a member of the left coset YH, prove that the left coset XH is the same as YH. Now, to do that, that looks suspiciously like we'll use one of the proofs. What was the proof number? Was it 47? Well, I think 47. Let me just check. It was that 3-part proof that we began the theories. Yeah, I'll write it out. Yeah, it's 47. No, 46. 46. I'll write it out. So it was theorem 46. Theorem 46.1. Part 1. So XH equals YH if and only if X inverse Y belongs to H. Right? Remember that from the theory session? So, given you got this kind of thing, and this was part, very probably we're going to use this in the proof. All right. So you told X belongs to YH. So X must be of the form YH. There must be some H belonging to this subgroup. Right? Call it H1 for this to be true. Right? You have to have that. If X is a member of this, X must be of this form. Okay. So from this, XY inverse is equal to H1. Right. Now that's not in the form we want here. So to get this in this form, into this form, let's what could we do? Take the inverse of both sides. Let's try that. So if we inverse both sides, right, and this will give you y inverse inverse, x inverse, so that's just y x to the minus 1 equals h1. Alright, I didn't do that last time. So if I so we've got x equals yh1. X. So we've got that. Right. So y inverse x equals h1. Well, I need to think a little.